Hello, I know Perrin has been introducing his lectures with woos, but I don't think I can physically produce that noise with my vocal cords. Um, yeah, sorry to disappoint. But yeah, welcome to CS161 lecture number 9. We're going to talk a bit today about public key encryption and digital signatures. So we're moving into the asymmetric world of cryptography today. Just a couple of announcements before we begin. You should have received these yesterday. But homework 3 was released yesterday, and it's going to be due next Monday. So we're trying to aim for a release Tuesday and have it due on Monday schedule for every week from now on. The last couple of weeks were a bit messed up because of the long weekends, but hopefully we should be on track for now. The midterm, it's happening. It's going to be next Tuesday. So we sent out an forum for if you have a conflict with this current time, we can definitely work with you to schedule an alternate time if this time doesn't work for you, because I know we have some students who are in other time zones and so on and so forth, and we don't want you taking it at like 2 o'clock in the morning. That would be a little ridiculous. The logistics are available at this link, and if you're not able to make the time, please fill out the conflict form as soon as possible. And just as a reminder, homework 2 is still on Gradescope. It is due today. So if you haven't worked on it yet, I recommend working on it and, in fact, finishing it. So yeah, last time we talked a bit about PRNGs. So as mentioned, randomness is hard to really generate because computers are machines that are meant to follow a predictable program. It's expensive to generate these. So generate true randomness. So what we want is an algorithm that can take this little bit of randomness and generate a lot of random looking bits. There are a couple of algorithms that we went into. For security, we want to make sure it's indistinguishable from actually random bits. And we also want to make sure that the adversary can't go back and view previous states of the PRNG just because, I don't know, maybe you generated a private key and we don't want the private key being revealed if the adversary ever compromises your computer. We talked about HMAC ARGB, which is an implementation of this, and we talked about an application, which is UUID, so unique identifiers for things. We also talked about Diffie-Hellman key exchanges. So just to recap, there are two parties, Alice and Bob. They both choose a private parameter, A for Alice and B for Bob. They raise their private parameters to the power of G. So G to the A and G to the B are their public parameters, and these are sent to each other. Because Alice and Bob know A and B, Alice knows A and Bob knows B, they can both derive G to the AB, and this becomes their shared secret. And the key is that Eve can't derive G to the AB using only G to the A and G to the B, which is why this is useful for a key exchange. This gives us forward secrecy, which means that if Alice and Bob both delete all the private material off of their computer, you can never recover the key, even if Eve later compromises their computer. And you can do it over some other mathematical groups as well, if you really want to, but we're not asking you to know any of the other groups for this class. Some issues are that it's not secure against a man in the middle, because if you receive some G to the something, you have no idea who generated that. It could be Mallory doing a man in the middle attack, and both parties have to be online. So it's kind of annoying if I'm on a plane and my phone can't generate my G to the B and send to Alice because I have no Wi-Fi. All right, so today we're going to go into the world of asymmetric cryptography, also known as public key cryptography. We'll talk a bit about how to encrypt things using public key cryptography, and then we'll talk about digital signatures, which is the integrity authenticity version of asymmetric cryptography, or the asymmetric version of integrity and authenticity. All right, so the interesting thing is, as we're talking about Diffie-Hellman, we already have a bit of public-private key stuff. You might have noticed that Alice and Bob, they can never share their A or B to anyone, but they were able to send G to the A and G to the B to each other. So we've already got a bit of public-private key stuff going on here, but we're going to formalize it a bit. So in a public key scheme, there are two keys. There's the public key, and this is known to everyone. So if I generate a public key and a private key, I can send this public key in the Zoom chat, post it on Piazza. It's totally fine. If Mallory learns it, it's okay because you can't use it to do anything that I wouldn't want you to do. By contrast, the private key should only be known to me. So this is the key that I want to keep secret, make sure that no one learns it. Otherwise, they can impersonate me and they can decrypt my messages. These are always going to come in pairs. So every public key is going to have some private key, and some private key is going to have some public key corresponding to it. So these have to go together. In general, I know for the schemes we've talked about before, with the exception of Diffie-Hellman, there's been a lot of XORs, a lot of bit shifting, a lot of adding. In the asymmetric realm, generally, we're going to be using complex number theory. So we saw in Diffie-Hellman, we used a bit of mod math. We'll see later on that some problems rely on factoring really large numbers. And as we saw last time as well, we talked about the discrete log problem, which is also sort of number theoretical stuff. Symmetric key, as I mentioned, uses XORs and bit shifts. And just as an aside, we're not going to ask you to like regurgitate these proofs on an exam. We're not too concerned that you know exactly how something like RSA works. We really just want you to get a feel for how to use these algorithms in general. In the asymmetric land, we're going to treat messages as numbers. So whereas before in symmetric key cryptography, we were talking about bit strings, here we're just going to deal with numbers. So before we were talking about like A and G to the A, those are all numbers. You can refer back to 6.2 and see if you want to think about how you would convert these numbers to actual bits, but it's not important here. Just imagine that everything is a number in asymmetric cryptography land. A benefit of this is, as you may have already noticed, we don't need Alice and Bob to share a secret anymore. Alice can just give Bob her public key, and Bob can use it to communicate with Alice without ever having to do a key exchange and without having to both share a secret key. Bob only has public information, and that's really useful for computer science in general, cryptography. A drawback is that it's a lot slower. So because this has a lot to do with number theory, it's just going to be really slow. Because CPUs are fast at XORing things, they're really fast if you want to add numbers together, but usually there's no CPU instruction that's like exponentiate this thing 200 times and then take it mod 20 or 200 something, I don't know. So just because of its nature, it's going to be a lot slower, and we'll look at how we can mitigate this a little bit later today. Any questions on, I guess, the public key framework in general for today? All right. In that case, let's dive into encryption. So in encryption, remember, because we're in public key world, we have a public key that anyone can use to encrypt a message. So if I want Perrin to communicate with me, I can just give him my public key, and then he can use that public key and encrypt messages and send them to me. And everyone has my public key. That's just going to be an assumption. Anyone can send me a message using only public information. We don't need to share a secret key or anything. I, as the recipient, I hold the private key, so only I can decrypt messages. So if an adversary intercepts a message between me and Perrin, from Perrin to me, the adversary can't use the public key to somehow decrypt that message. You can only use the private key. So it's really interesting in that way. You can use the key to encrypt something, but you can't use it to decrypt, and vice versa, almost. So we'll present to you the formal definition for a public key encryption scheme. We're going to have three main parts, similar to the symmetric encryption scheme. There's going to be a key generation algorithm. So this is going to be the algorithm that generates your keys, and it outputs a pair of PK and SK. So PK is our public key, and SK is our secret key or private key. We have an algorithm for encrypting. So notice that this algorithm takes the PK. So it's not just K, where like for a symmetric algorithm, it's PK, and encrypts M and outputs the ciphertext C. And as before, we'll have a decryption algorithm, which takes in the private key. So notice it takes an SK, not PK, and it outputs the original message M. Some properties that we want. This one's fairly self-explanatory, but for correctness, we want to make sure that if we encrypt something, you get back the original message when you decrypt it. Otherwise, it wouldn't be very useful as an algorithm. This is the formal definition. You don't need to worry too much about it. It's just saying for all keys, the decryption of the encryption is just the original message. For efficiency, we're saying it still needs to be fast. So we still don't want it to take like the lifetime of the universe to compute. It's not going to be as fast as symmetric encryption, but it still needs to be reasonable. And for security, formally, it's a little bit different from NCPA because you don't need to ask Alice to encrypt things for you because you have the public key. You can just encrypt things yourself. So the only thing that you really need Alice for is to choose one of the two messages to encrypt and encrypt that one. So the definition is slightly different. It's technically called semantic security, but it's pretty much the same thing as NCPA, and we're just going to call it NCPA from now on. So we don't have to think about, is semantic security the same as NCPA? Because it's not, but it is. So yeah. Questions on this definition? All right. Okay, the first scheme we'll talk about is called El-Gamal. Why it's the second bullet point on this list, I don't know, but it would have been too much work for us to go back and flip these two bullet points in the entirety of the previous lecture slides. So we're just gonna start with the second algorithm on this list. For El-Gamal, it's going to be very similar to Diffie-Hellman. So Diffie-Hellman is useful. It lets Alice and Bob share some secret. But this secret is random, so that doesn't really help us on its own. The AB doesn't actually mean anything. It's just some secret that's shared. And for Diffie-Hellman, they both have to be online. So we're going to try to tweak this algorithm a little bit to let us encrypt messages in a way that Bob can generate his key and then go offline. And then Alice can just do her thing to encrypt things while Bob is offline. So here's the protocol. For the key generation, Bob is going to generate some private key, call it B, and a public key, it's going to be G to the B. So you might already start to see some similarities here with Diffie-Hellman. In fact, this is basically Bob's part of the Diffie-Hellman key exchange. He's computing this public key, which is that G to the B from the Diffie-Hellman. And of course, it's going to be mod P. For encryption, so this encryption takes in the public key G to the B. Do keep in mind that you can't figure out what little b is here. It's just taking in G to the B as one blob, and you can't somehow separate it. To encrypt a message M, what Alice is going to do is she's going to generate some random number R, and she's going to compute G to the power of R mod P. So again, we see some similarities with Diffie-Hellman here. Alice has just generated a private one-time key for this encryption and computed G to the power of R, which is the public component of that R. And the intuition is Alice is doing her part of the Diffie-Hellman exchange. In order to encrypt the message, what we're going to do is we're going to take this G to the B and we can raise it to the power of R. So this whole thing is G to the BR. So it's that secret, shared secret from before. And when we multiply it by M, we're essentially hiding the value of M. You can basically think of it as we're multiplying M by some random value. So that random value, that resulting blob of bits is something multiplied by a random value, so we can't get back the original value of M. Bob is sharing G to the B. So I guess we haven't written it out fully everywhere, but G to the B, everything here is implicitly mod P. We're just sort of working in modulo land, but yeah, everything here is mod P. You can just assume it's always mod P. Same thing with this message, but we have explicitly put mod P here. Good question. Yeah, the intuition is we multiply M by some random value, so we're now hiding the value of M. And finally, Alice is going to send her ciphertext in two parts. So we have a C1 and C2 here. This just means that the ciphertext has two parts, and Bob is able to see like, oh, this is part one and this is part two. Part one that Alice sends is that G to the R from before. So this is just the public component of that Diffie-Hellman. And part two is going to be the ciphertext, the actual ciphertext that she computed, which is the value of M multiplied by G to the BR, which is some random value. So we're hiding the value of M. In order to decrypt, we're going to need to take in the private key, Bob's private key B, the G to the R, so this is part one of the ciphertext, and M times G to the BR, which is part two of the ciphertext. In order to reverse this, we really just have to go backwards. So we know that we can derive g to the br, because we have b and we have g to the r. So we compute g to the br, that's the same as g to the r, to the b. And what we're going to do is we're going to compute the inverse of that. So in mod math, you can divide things kind of. For the purposes of this class, you can just assume you can divide things in mod p land. So what we'll do is we can divide out this g to the br by multiplying by g to the negative br, which is what we're doing here. And here we'll get back the original message. So these two parts cancel out and we get back the original m. So intuition, Bob just derives the shared secret, takes the inverse of that, uses that to divide out the original g to the br to some random value, and you'll get back the original m. Does this make sense? Any questions? All right, let's talk about the security of the scheme a little bit. Remember that the Diffie-Hellman problem states that if you're just some adversary, you're given g to the a and g to the b, it's hard for you to recover g to the ab. This is one of the things that we're relying on because we're sending g to the b and g to the r in plain text. So g to the b, which is capital B, is the public key, so everyone knows that. And when Alice is sending g to the r as the first part of the ciphertext, that's also readable by anyone. So because we're sending g to the b and g to the r, we want to assume that g to the br is hard to recover because that's what we're relying upon for this scheme. Otherwise, the adversary could just divide out g to the br and recover m. So we're in LGML, we're sending these values over the secure channel. And we're assuming that Eve can't derive this. So we assume because the Diffie-Hellman problem is hard, Eve can't derive g to the br, so Eve can't derive m. That's sort of what this is relying upon. There are some issues with this. So could anyone think of how Eve could break in CPA? And I'll go back to the definition for a moment. Is there some message that if it were encrypted, it would be really obvious that Alice encrypted m? M equals 1, okay. So if m equals 1, then, okay, and 0. So those are the two options that you could really use feasibly. I've also got g to the br in chat. So remember that g to the br itself is never sent in public. So Eve doesn't know what g to the br is, so she can't actually recover that. But the answers of m equals 0 and m equals 1 is exactly correct. If Alice encrypts m equals 1, then, oh wait, actually. Actually, now that I think about it, I think m equals 1 wouldn't work because then all Eve would see is g to the r and g to the br. But usually we assume that it's hard to tell if this is g to the r and g to the br or something else. So actually m equals 1 wouldn't work in this case, but m equals 0 is exactly correct because in this case, C2 would just be 0 times something else. So you can assume if C2 is 0, Alice just multiplied by 0, so Alice encrypted 0. So we can really easily break this scheme. Does that make sense? I know there were a couple answers and I changed my mind on one of them, but yeah, okay. What this means is that if we want LGML to be in CPA secure, we have to add some modifications to the scheme that make it semantically secure. I didn't change the term here, but it's in CPA secure. There's another problem as well, that the adversary is really easily able to tamper with the message. So remember, C1 and C2 are two parts of the ciphertext. Let's just say that we want to manipulate this message, and I'll sort of walk you through what the manipulation is and what the final output looks like. So for C1, we're just going to leave it as it is, because that's just g to the r, and it wouldn't really help us to modify that. And for C2, we're going to multiply that by 2. So C2 prime equals 2 times the original C2. If we expand this out, we see that this means that this is 2 times m times g to the br. And when Bob goes to decrypt this, he's going to cancel out this g to the br here. So what Bob will see is that, oh, it looks like 2 times m was encrypted. And this might be a problem if, I don't know, maybe Perrin is saying to me, you owe me $10, but someone is sitting in the middle and they like Perrin, I don't know. So what they'll do is they multiply the message by 10. They don't know what number Perrin originally sent, but they know they can multiply that number by 10. So suddenly I receive something and it's like, oh, you now owe me $200. I'm like, oh, wow, this must have come from Perrin because I'm assuming it came from Perrin, but someone actually modified it. So the issue with Elgamal is it's really easy to change the value in a way that's predictable. How would it be hard for Eve to find g to the br if m is equal to 1? Yeah, so really it's sort of the same thing that g to the r and g to the b, it's hard to find g to the br. And there's an additional assumption that we won't talk about, that it's hard to distinguish g to the b, g to the r, and g to the br from g to the b, g to the r, and some random number. It's hard to distinguish those two. It's a different Diffie-Hellman problem that we won't talk about, but yeah, don't worry about it too much. Yeah, all right. And knowing g to the br isn't even useful since r isn't reused. Yeah, that too. You know, if Eve learns g to the br, she can decrypt that one message, but you know, generally we don't really want her learning that. So yeah, even if she sent m equals 1, then that g to the br wouldn't help anyone else. Is g to the negative br the multiplicative inverse of g to the br mod p, actually? Yeah, because p is a prime number, we assume that all numbers have an inverse. So g to the negative br times g to the br, if you apply your law of exponents, that becomes g to the power of negative br plus br, which is g to the power of 0, which is 1, which is why multiplying and then multiplying by the inverse is sort of the same as dividing. It's sort of complicated, and if you really want to study more number theory, you can go take CS70, but we're not requiring too much number theory background for this class. All right, very good questions. I know number theory is very weird to wrap your mind around sometimes, but all right. All right, so with that, we're going to move into our second encryption scheme today. So RSA encryption, this is definitely the one that more people have heard of. I know when I took this class, Elgamal was like, I've never actually heard of this before, but RSA was like, oh yeah, I've seen that. You might have used it if you've SSH'd into a server before. It's pretty common nowadays. So for our definition, we're going to have a keygen algorithm, and there's about to be a lot of math, so just sit tight. And if you don't follow, that's also okay. You don't need to worry too much about this slide. What we're going to do is we're going to choose 2 large primes, P and Q. You can really just do this by generating a bunch of random numbers until one of them is prime, or there are other ways you can do this as well. Doesn't matter too much. We're going to compute n equals the product of P and Q, so P times Q. And in this case, that's supposed to be a capital N, but in this case, n is usually between 2,000 and 4,000 bits long. This is usually what you see when you see like 2048-bit RSA key or 3072 bit RSA key. Next, we're going to choose some value of E, and I'll walk you through how we choose this right now. We require that E is relatively prime to P minus 1 times Q minus 1. This means that if we know the values of P and Q, we subtract 1 from both of them, multiply them together, and we just make sure that E and this product don't actually share any factors with each other. So we can pretty easily do this just by making sure E is some prime number, and it's pretty likely that E will be relatively prime. And we also require that E is some sane value, so we don't want it to be 1 because that's not going to help us very much, and we don't want it to be this value, as you'll hopefully see in a moment. And then we're going to do something funny. We're going to compute the inverse of E mod P minus 1 Q minus 1. So again, if you don't know why, it's okay, but we'll get to it in a moment. The way we do this, if we just want to compute some inverse of something mod something else, we can use something called the extended Euclid's algorithm. This is from CS70, but it's out of scope, so you don't need to worry about it if you don't remember extended Euclid's. Our public key is going to end up being N and E, and our private key is going to end up being this D. So this D that we computed using this fancy algorithm is what is private, and then N and E are public. So this product here and the E that we chose. All right. For encryption and decryption, it's all relatively simple. What we're going to do is output, take some message and raise it to the power of E mod N. And if we want to decrypt, we'll take that message, raise it to the power of D, and we'll get back our original M. Oh, we'll get back our original M, but you'll see that in a moment. What you see right now is it's C is M to the E, so C to the D is M to the E to the D. We've basically taken M and raised it to the power of E and then raised it to the power of D when we decrypt it. Okay, so it's like, well, why does this work? We're just raising a bunch of numbers to a bunch of powers. Like, there's no way this could possibly get back to the original message, right? I also forgot to make this N capital as well. Okay, so I'll walk through why this is correct. The first thing that we need is something called Euler's theorem. Here's what we want to prove. M to the ED is equivalent to M mod N. So if we raise it to the power of E, raise it to the power of D, we get back our original message. Euler's theorem states that a to the power of phi of n for some n is equivalent to 1 mod that n. So this phi represents something called the totient. I actually don't know how to pronounce this. I've never had to say it aloud. Phi of n is the totient function of n. And if n is prime, then the totient function of n is actually just n minus 1. So this is Fermat's little theorem, which was also covered in CS70, but you also don't have to worry about that. But if you did take CS70, this is sort of just a generalization of FLT. If n is semi-prime, so if it's a product of 2 prime numbers, then the totient function is actually going to be p minus 1 times q minus 1. And this actually generalizes to even more prime numbers. But this is what we're working with. So for now, just assume that if n is a semi-prime, its totient function is p minus 1 q minus 1. All right. This is all out of script CS70 knowledge, so don't worry about it too much. The thing to notice here is that we chose D as the inverse of E mod P minus 1 Q minus 1. So if we rearrange a little bit, E times D, because the inverse is, it's going to be equal to 1 modulo P minus 1 Q minus 1. This is just an alternate way of saying E times D is equivalent to 1 mod the mod phi of n. And this is going to be really useful in a moment. So if we remember our definition of what mod actually means, this means that E times D is equal to some multiple of k, or some multiple of phi, so phi times k for some integer k, plus 1. All right, because their inverse is mod phi. So E times D is equal to 1 mod phi, so that's k times phi plus 1. All right, so if we now rewrite our original thing that we want to prove, E times D is just k times phi plus 1. So this is really m to the power of k times phi plus 1. Now, if we go and just rearrange this using our properties of exponents, we know this is m to the k times phi times m to the power of 1. And if we go all the way back to our Euler's theorem over here, m to the power of phi of n mod n, all of this is just 1. And we're raising 1 to the power of k. So all of this just becomes 1. And m to the power of 1 is also just m. So this all reduces down to m is equivalent to m mod n. And that sort of begins to explain why we use this really complicated algorithm, because we needed to choose some, like we could choose E pretty much however we wanted, and then we needed to choose D such that it fulfills this constraint here. And because this constraint is fulfilled, that means that we can use Euler's theorem and know that, okay, we're just multiplying by 1 a bunch of times because we have m to the power of k times phi. And then we'll have that extra plus 1, which means that we'll get back to our original message. So all this really means is that if we take m, raise it to the power of e, raise it to the power of d, we'll get back our original n. And this is why you can't use the same key to decrypt, because if we raised it to the power of e again, then we would just get m to the power of 2e, which is not really useful to us. All right. This math isn't really in scope. We should probably make this slide blue, Perrin. But any questions or? All right. If you're just staring at this and are confused, that's okay. You're probably not the only one. And we're not going to test on this, so we'll go back and make the slide blue. But for the security of RSA, we're going to define something called the RSA problem. So this is pretty straightforward, and clearly I forgot to capitalize this m as well. Given n and m to the power of e mod n, we're just going to say it's hard to find m. So this is really just an adversary trying to decrypt a message. If we give them the public key n and the ciphertext, it's hard to find the original value of m. We know that it's no harder than the factoring problem, because if you can factor n into p and q, then you can just go through the same process as the keygen algorithm to figure out what d is and then use that to decrypt the message. So it's no harder than the factoring problem. And the current best solution is to factor n. So we don't know of an easier way other than factoring n. So for now, to the best of our knowledge, it's as hard as factoring n, but we don't know if there's an easier way. So it's not a rigorous, it's as hard. It's a currently the best implementations that we have just factor n. RSA stands for Rivest, Shamir, Alderman, just the letters of the initials of the creators of the algorithm. You can look it up because I don't want to accidentally misspell one of their names. Mainly Alderman. I know how to spell Rivest and Shamir, but not Alderman. So, but yeah, maybe Perrin can look it up. This means that if the RSA problem is as hard as the factoring problem, then the scheme is secure as long as the factoring problem is hard. This is a general assumption that we rely on. We just assume that the factoring problem is hard. If I gave you a number like, I don't know, what are the prime factors of 299? There aren't that many good solutions to solve for those prime factors. Most of them are still going to take a really long time to run, and that's why we can rely on the security of RSA. Some issues with this. So is this in CPA secure? And that is a question. And does anyone want to pose yes or no, and maybe why it's not, or it is in CPA secure? What's missing from, what's missing that would make, that any scheme needs in order to even have a hope at being in CPA secure? Yes, this is a deterministic algorithm. All we're doing is raising something to the power of something. We're never introducing any randomness. So if I encrypt the same message twice, I'm going to get out the same message twice. So, nope, wrong slide, this one. Another thing that also happens is that if we send the same message with two different public keys, we also leak a little bit of information. This isn't usually something we worry about too much. I forgot to capitalize this N as well. Clearly, I did not thoroughly check these slides. But if I choose different values of E, if I get some small value of E, then this is going to end up leaking information. Because if my message is 2 and E is 3, and I encrypt that, I know that my ciphertext is going to be 2 to the power of 3, which is 8. And any adversary can clearly see, oh, if the message is 8, or if the ciphertext is 8 and the key is 3, then I can probably assume that I can just take the cube root of it and get back to the original value. So this will also leak information. And E is actually usually small. So this is for efficiency reasons, because we have to we don't want to exponentiate something to a really large number. So it's often some constant, which is either 317 or 65,537. These are just the commonly chosen values. And there's also a side channel. There are also many side channels when it comes to RSA encryption. Oftentimes, poor implementations will take different amounts of time to decrypt the message depending on the message and depending on the private key. So if an adversary can see how long it took for you to decrypt a message and you're using a poor implementation of RSA, they can start to learn things about the message or about the private key, or both, just because whoever implemented it poorly. So I guess the takeaway here is don't roll your own crypto, just use a trusted library. This has been used before. So OpenSSL used to have a poor implementation of RSA, and they used it to break RSA encryption for a large key that is infeasible to factor. So we managed to break it purely through a side channel attack. The result of all of this is that we need a probabilistic padding scheme. So padding isn't the same thing as padding in AES. We're just saying we need some way of transforming the message that A, introduces randomness to solve this. B, make sure we always get some sort of large number, so that if we exponentiate a really large number, that mod is definitely going to kick in, so it wraps around. And the probabilistic padding scheme is also going to help mitigate the information leakage, because we're always going to be encrypting large numbers that are all sort of in the same order of magnitude. All right, we won't get into, or the padding schemes aren't going to be in scope for this class, but I'll introduce them to you anyway, just because I think they're really interesting. So we have something called OAEP. This stands for Optimal Asymmetric Encryption Padding, which I think was just a name devised by someone who wanted to add as many syllables to a term as possible. Not really. But this is just it's not a variation of RSA, I guess that's a typo, but it's a padding scheme that introduces randomness into the plain text. And we'll see in a moment that it's actually really just an encryption algorithm that also includes the key. So it's really easy to decrypt because the key is just part of the message now. So again, this is not padding for symmetric encryption. This is just instead some way of transforming the message, because remember, we're dealing with numbers here instead of strings of bits. RSA can really only encrypt random looking numbers. So what we're going to do is we'll take the message and we're going to encrypt it with some key. And this key is known, it's fixed. So we don't have to worry about, sharing a secret key with someone else. It's just a fixed key known by everyone. But encrypting it with that known key is still going to make it look random. So when it's input to RSA, it'll still be fine. All right. This is a diagram, and I'll walk you through this diagram for each step of padding. So we're going to just have two constants. So we have a K0 and a K1. Now, these are really just lengths of different parts of this full block here. And we have two different hash functions, G and H. We impose the requirement that n can only be a certain number of bits long. So I know we're dealing with number theory, but now we have to go back into bits land, just because we're going to be appending things, and appending doesn't really make sense in number theory land. So we require that n is only the number of bits that can be encrypted by RSA in total, and then we're going to take off a little bit just because we need that for the padding and to make sure the number is large. G is going to produce a hash that is this long, so it's going to produce an n minus K0 bit hash, and H is going to produce a much shorter hash. It's just going to produce a K0 bit hash. So I think this diagram is what makes it clearest. Basically, you have three parts. This is n minus k0 minus k1. This is k1. This is k0. All of this makes up n. G produces a hash that is this long, this x here, and h produces a hash that is this long. All right. First thing that we're going to do, we're just going to pad m with a bunch of zeros. This helps make sure that that the bits of m are going to be all the way to the left. So this is going to make this a large number so that we don't run into the problem with small numbers. This also helps us, oh, I might have mixed it up a little bit, but this helps us sort of make sure our message wasn't tampered with. It doesn't provide integrity in that sense, but it really just helps us determine when I decrypt using RSA, I should see a bunch of zeros here, otherwise something has probably gone wrong. Next, we're going to generate a random string R. So that's this yellow input over here. And we're going to compute this x, so this part of the output, is equal to m padded with a bunch of zeros, and then XOR it with the result of hashing G. So again, this diagram is a lot easier to look at than this equation over here, but we'll take M and these zeros, concat them together, and XOR it with the output of G. And remember, G is a hash function. Next, we are going to sort of go the other way. So we have this output. This output is what created X here. And we're going to take that, put it through our other hash function H, and then we're going to XOR that with our original value R. And this produces Y. Our final output is going to be just X concatenated with Y. And all of this is going to look random. The intuition you can kind of use here is that R is random, that hash of R, so G of R is also going to look random. And likewise, this is random. So we're XORing something with something random. So X looks random and Y looks random. And that's all we really need to be able to input that into RSA. To unpad, you might be wondering, we're using hash functions. Shouldn't it be impossible to go backwards through a hash function? And you're kind of right. That's what these arrows here represent. We can't just go back and directly reverse this hash. But notice that we always have one of the inputs to the hash function available to us. So we can just take this X, we're going to hash that again, and then we have this part and this part of this XOR, so we can go backwards and recover the original R. So that's our first step. We'll compute R equals Y XOR the hash of X, H of X. So we'll get back our original R. And now that we have our original R, this was our input to G. So we can now take G of R, now that we know R, XOR that with the X from our padded ciphertext or padded plaintext, and get back the original M and then with a bunch of zeros. So we should make sure that M still ends in a bunch of zeros. Otherwise, something has probably gone wrong, or maybe someone messed with our message. Error out if it doesn't pass that step. And if not, then we have our original message M here. So this is a very interesting construct. Again, G and H are irreversible. We can't get back to the original thing because it's a hash function, it's one way. But because we can recover their inputs, we can still work our way back up through this ladder. This whole construct is known as a Feistel network. This can be used for encryption in general. And I guess the intuition here is that you're XORing a bunch of things with a bunch of other things that are kind of random. So if G and H, these two hash functions actually depend on some secret key, then we can use this as like a proper block cipher, and then we can start adding CPC mode or counter mode to that and make it a full-on symmetric key algorithm. So this has been done before. The data encryption standard DES was sort of the main symmetric key algorithm before AES. It's now out of use, but this is what was used before AES, and that had this Feistel network. It just had a lot more of them. Instead of 2 rounds, I think it had 12. I actually don't remember off the top of my head. It might be 30. Sorry. But basically, if you want to use RSA, you should never use plain RSA. You should use something called RSA OAEP, which just uses OAEP to pad and unpad the message so that the input to RSA looks random. Questions on this? they're blue slides, so it doesn't matter too much. I just think it's really cool because you're basically encrypting something before you encrypt it just to make it look random. And it's like, oh, that's a really cool way to do it, at least in my opinion. So as we talked about earlier, RSA and LGML both have an issue where they're really slow and they can only encrypt messages up to the modulus. So notice, we can only encrypt small messages. Because of that modulo operator, if I try to encrypt something larger than that modulo, I'm just going to end up wrapping around. So my message is going to end up having to be smaller than the maximum value, than the value of the modulus, otherwise I wrap around. So that's issue one. We are stuck with fixed length messages. Issue two is that there's a lot of math, and computers are slow at math, at least versus XORing and whatnot. So this means that asymmetric really just doesn't work for large messages. If I have a really long, say 1 GB file, and I want to encrypt that with RSA, I should not like break it up into a bunch of chunks and then encrypt those individual chunks, because that would take forever, even with like a powerful processor. That's just pretty infeasible. What we're going to do instead is we're going to introduce something called hybrid encryption. And Nicholas, I see your question in the chat. I'll get to it after I finish describing this. What we do is, instead of encrypting the message directly, we can generate a random symmetric key. This is just, random using a PRNG or whatever. Use that to encrypt our message. And, because we can't just send the symmetric key, otherwise the adversary will learn it, then we take that symmetric key and we encrypt it with our asymmetric encryption, with our public key encryption. So the result here is that when Bob receives the message, he's going to receive two parts. He's going to see, oh, here's the encrypted symmetric key, and then here's the ciphertext encrypted with that encrypted key. So Bob is going to decrypt the symmetric key and then use that symmetric key to actually decrypt the message. And this solves all of our problems. Now we can encrypt a lot of data using symmetric encryption, and we still have, we don't need to somehow share a secret key with Alice because now we're using public key encryption. So all of this is really useful. All right, questions on this, and then I'll get your question, Nicholas. And thank you, Sergio, for putting the RSA names in chat. All right, there's a question in chat going back to OAP about, does everyone know R? So it's easy for anyone to recover R, because remember, for OAP, at least on its own, OAP is just a padding algorithm and everyone knows it. There's nothing secret about this. So if someone just gave you X and Y, these outputs of padding, you could easily just go back through and unpad it yourself. But R is chosen randomly as part of this algorithm because we want to introduce some sort of randomness. So this is where randomness comes from. We choose a different R each time we encrypt the message, and that makes it no longer deterministic. R is, yeah, you can think of it like an IV. It's basically the thing that introduces randomness. I don't think you'll ever see it called IV anywhere in the literature or Wikipedia or whatever, but yeah, you can think, I would say that both the IV for block ciphers and the R in OAP serve the same purpose in that they introduce randomness. Yeah, sorry, just trying to be technically correct there, but I might still be wrong anyway. But yeah, so that concludes our discussion on how we encrypt things asymmetrically. Now you know how to send a message to me and Perrin, and we'll be posting our public keys shortly. Or maybe not. So that's great. We have a bunch of benefits from asymmetric cryptography in general. Now we're going to take that and we're going to apply that to integrity and authentication and authenticity. So we don't need to share a secret key, and digital signatures are the asymmetric way of doing cryptography when you want to provide integrity and authenticity. So For now, just assume that Alice and Bob can communicate their public keys without Mallory interfering. I realize this is yet another assumption. Before we were assuming Alice and Bob share a secret key. Now we're assuming Alice and Bob can get their public keys to each other. But we'll deal with that in the next lecture. Just make this assumption for now. So for digital signatures, we have 3 parts. I know there's sometimes just a lot of parts to things, but it's just part of the official definition or technical definition. We need some way of generating the key. So this is the same thing as before, but in this case, the public key is going to be something called the verify key. And SK, the secret key, is going to be the signing key. Now we need some way to sign the message. So we're actually going to end up signing the message with our secret key. So this sign out algorithm takes an SK and the message M, and it outputs a signature. So the signature is bound to the message M, and you need the signing key in order to produce the signature sig. We also need a way of verifying that the signature is actually correct, because what good is a signature if you can't somehow check it? So for a signature algorithm, we need a verify function. And this is going to take in the public key. So anyone's allowed to verify a signature. It'll take in the message M because you need to verify that this is the message that they actually signed. And then you'll take in the signature because it's the signature that I need to verify. And this is just a fancy way of saying that it's going to take in, that it's going to output either 0 or 1, basically either true or false. It returns true, it outputs 1 if the signature is valid for that message, and 0 if it's invalid. Properties. Can anyone guess what the first one is? All right, maybe not. Yeah, correctness. You should, if you generate a signature, it should verify correctly. I think that's pretty self-explanatory. There's the formal definition. We also want to make sure that signing and verifying should be fast. So again, not quite as fast as something like Max, but still not so slow that you're gonna let the universe burn before it finishes. And for security, it's the same thing as Max, where it's EUCPA. Basically, the adversary can't generate a signature for a message that they didn't query from Alice. So the adversary is allowed to ask for as many messages and have them signed, and then they have to somehow generate a signature for a message that they didn't ask for. All right, makes sense? It's basically just Max, but with public and private keys, and the public key is used to verify and the private key is used to sign. All right. Probably should have taken a break at some point. That's okay. We're almost done. For RSA signatures, you might notice this is the same algorithm as before, and that's kind of because it is. For RSA encryption, what we have is the guarantee that for our E and D, if we take any message, raise it to the power of E, and then raise it to the power of D, we're going to get back our original message. But there's nothing special about using E first or using D first. If we encrypt, instead of using E, if we encrypt it using D, then anyone can decrypt using E, because everyone knows what the public key E is. So anyone can decrypt that message. And sort of what we're relying upon is if they get back to the original value of something, then you can assume, okay, they must have encrypted this with D, and that was their act of signing this message, because no one else could have done that because no one else has D. Notice that if I give you some x to the power of D and also just x, you still can't recover D, and this is because of discrete log problem. So you can't recover, given a signature, you can't possibly recover the value of the private key unless you break discrete log. All right. So for the key generation algorithm, it's the same as RSA encryption. You're going to have a public key, which is N and E, and you're going to have a private key, which is D. For the signature algorithm, what we're going to do is we're going to compute the hash of the message, and then we're going to take that to the power of D. It sort of has the same intuition of you don't want to encrypt small messages and you want to make sure your inputs to RSA are always random looking. So we're going to hash the message and then raise that to the power of D, and that's going to be our signature. When we want to verify, we need to take in the public key, so both E and N. We'll take in the message M, and we'll take in the signature that was outputted from the sign function. What we want to do is we hash the message ourselves, so we'll get the hash. We can do that ourselves. We'll raise the signature to the power of E, take that mod N, and we want to make sure that this value is the same as before. So if we take the power, the signature is H, is the hash to the power of D. So the hash to the power of D to the power of E should just get back the original hash. So we hash the message ourselves and make sure that the hashes match. All right. I feel like the slide was duplicated somewhere, wasn't it? I'm not sure how that happened. Yeah, that slide was duplicated twice. All right, that's the definition of RSA signatures. It's basically just the same thing as encryption, but encrypting using the private key. Any questions on this? All right. Well, that actually brings us to the end of today's lecture. We just have a quick summary for you. So we talked about public key cryptography today. We have two keys, one undoes the other. For encryption, one key is going to encrypt and the other is going to sign. So this gives us the same security properties as symmetric encryption. We talked about El-Gamal, which is based on Diffie-Hellman. We have G to the B, which is the public key, and we have G to the R, which is part of the ciphertext and is different for each message. But because Bob basically has a long-term G to the B, this is basically just Diffie-Hellman, but now Alice can do it while Bob is offline. And it's not in CPA secure on its own. You do want to have some padding scheme. RSA is a little bit more finicky. We're going to have some E to the E and D, such that if we take a message, raise it to the power of E, raise it to the power of D, we'll get back the original message mod N. And this is also not in CPA secure on its own. We want to have the OAEP padding scheme that we talked about earlier. If we want to encrypt large messages using public key cryptography, you should not encrypt the message directly. Instead, what you can do is just encrypt a symmetric key, and then that symmetric key is used to encrypt the message using AES, CVC or counter mode. You can use your own favorite symmetric key algorithm or a symmetric key encryption algorithm, but that's how you should do it because it's fast and it gives us the benefits of public key encryption. And finally, we talked a bit about digital signatures. So this is the asymmetric version of integrity and authenticity. And we talked about RSA, which is the same as RSA encryption, but you're encrypting the hash of the message with a private key so that anyone can verify it with the public key and hash the message themselves and make sure that the hashes match. Should you do sign then encrypt like in symmetric? No. In symmetric, you should use encrypt then MAC. So in asymmetric, you should use encrypt then sign. Sorry, that was a very harsh no. I'm sorry about that. But you always want to make sure you're encrypting and then applying either a MAC or a signature. In general, it's encrypt then authenticate. Any other questions? All right. If not, I know we ended a bit early today, so you can just feel free to head out or stay around if you want to chat. I think we're gonna, I don't know if there's any parts of this lecture that we're gonna upload to the videos today, but yeah, see you around.